Welcome to this video about Problem 4 of EGMO 2020. The problem statement reads as follows. A permutation of the integers 1 to m is called fresh if there exists no positive integer k strictly less than m, such that the first k numbers in the permutation are 1 to k in some order. Let fm be the number of fresh permutations of the integers 1 to m. Prove that fn is at least n times fn minus 1 for all n greater or equal to 3. Now, in order to clarify things a little bit more, let's consider a couple of examples. The permutation 2, 3, 1, 4 is not fresh. Its first three entries are just the numbers 1, 2, 3 ordered as 2, 3, 1. If we look at the permutation 3, 1, 4, 2, however, by checking the requirement on its initial segments 3, 3, 1, and 3, 1, 4, we see that it is, indeed, fresh. Now, how to go about proving the inequality from the problem statement? In this video, we'll discuss two solutions that stem from the same basic idea. Could we explicitly construct n different fresh permutations of the numbers 1 to n from each fresh permutation of the numbers 1 to n minus 1? Let's look at our example, the permutation 3, 1, 4, 2, which is fresh. We'll be thinking of 4 as n minus 1 and try inserting 5 while attempting to keep the permutation fresh. For example, you can check that the permutation 5, 3, 1, 4, 2 is still fresh. So is the permutation 3, 5, 1, 4, 2. In fact, we obtain a new fresh permutation by inserting 5 in any position, except, and here's where we need to be a little bit careful, in the last position. The permutation 3, 1, 4, 2, 5 is not fresh, as its first four entries are the numbers 1 to 4. Let's state our construction in general. Given a fresh permutation sigma, whose entries are sigma 1 to sigma n minus 1 in this order, and an integer k strictly between 0 and n, we construct the permutation tau obtained by inserting n into sigma in position k, that is, immediately before sigma k. We claim that tau is fresh. Indeed, let's consider the first I entries of tau. If I is strictly less than k, then the first I terms of tau are sigma 1, sigma 2 up to sigma I. They cannot be the numbers 1 to I in some order because sigma is fresh. If I is between k and n minus 1, the first I entries of tau include n, which is not a number between 1 and I. So what have we done so far? For each of the fn minus 1 fresh permutations of the numbers 1 to n minus 1, by inserting n into each possible position except for the last one, we have built n minus 1 fresh permutations of the numbers 1 to n. It's quite clear that we've constructed n minus 1 times fn minus 1 fresh permutations in total, because looking at the table above, no two permutations in the same column can be the same, n is in a different position, and no two permutations in different columns can be the same. Erasing n yields a different permutation of the numbers 1 to n minus 1. Of course, we aren't done. We're still missing fn minus 1 permutations in order to solve the problem, and we need to come up with some new idea. So what fresh permutations are we still missing? Something that might be helpful is to notice that none of the permutation we constructed end in n-1, because none of the original permutations did. They wouldn't have been fresh otherwise. However, a fresh permutation of the numbers 1 to n may very well end in n-1. In order to construct some fresh permutations that do, let's go back to our example. Something we could have done, instead of immediately inserting n, was to move n-1 to the last position and insert n into the position it used to occupy. Like this. You can check that this permutation is fresh. In general, given a fresh permutation sigma of the numbers 1 to n-1, replace n-1 by n and add back n-1 at the very end to obtain a permutation Tor. The permutation Tor you obtain is fresh. Indeed, exactly as before, consider its first I entries. If I is strictly less than the original position k of n-1, then they cannot be the numbers 1 to n by freshness of sigma. If I is between k and n-1, then Tor has n within its first I entries, so we're done. Going back to our table, we get to add a new row, which is precisely what we wanted. The added permutations are fresh and all different, and the fact that they end in n-1 implies that they do not coincide with any of the permutations we already constructed. We have created a list of n times fn-1 distinct fresh permutations of the numbers 1 to n, so we have solved the problem. This is the official solution that we have labeled as Solution A. Let us briefly discuss how we can use essentially the same ideas, in particular the last construction, to come up with another solution more along the lines of official Solution B. Let's go back to our example. What we did to come up with fresh permutations for the last row was to replace n-1 by n in a fresh permutation of the numbers 1 to n-1. Then we placed n-1 at the very end of the permutation. But the truth is, we didn't really need to do that in order to keep the permutation fresh. In fact, we could have placed n-1 in any position, and the permutation would have stayed fresh regardless. That brings us to the following general construction. Given a fresh permutation sigma of the numbers 1 to n-1, choose k between 1 and n. We claim that the permutation Tor obtained by replacing n-1 with n and inserting n-1 in position k is fresh. So in order to show this, suppose Tor is not fresh. In particular, suppose the first I entries of Tor are 1 to I in some order, where I is some positive integer strictly less than n. Now, can I be n-1? The answer is no. That would mean that the last entry of sigma was n-1, which would make sigma not fresh. But then, can I be k or more while being less than n-1? Again, no. This time because n-1 is within the first I entries of Tor and isn't a number between 1 and I. Finally, can I be strictly less than k? Well, no. Either the first I entries of Tor are the first I entries of sigma, but sigma is fresh, or if they aren't, it's because they include n, which means they can't be the numbers 1 to I. So we've shown that Tor is fresh. This time, we've managed to construct n times fn minus 1 distinct fresh permutations of the numbers 1 to n in one go. If we look at the table above, whose last row is the one from solution A, permutations in the same columns differ by the position of n minus 1, and permutations in different columns yield different permutations if we erase n minus 1 and change n to n minus 1. Again, we're done. We hope you enjoyed working on this problem. Don't miss a separate video presenting another 2 solutions, less constructive and more computational.